start. So today is the last lecture on surrogate modeling, which means from next week after Diwali break, we will start something new. Now in surrogate modeling, if you go back to the first lecture of surrogate modeling, we decided what are the important steps in surrogate modeling. One of that was deciding the surrogate model to use. And we have spent 10, 12 lectures, I think. I don't remember the exact number, but let's say close to 10 lectures talking about different surrogate models, starting from response surface method, where we spent 1 lecture, polynomial chaos expansion, I think we spent 4 lectures, and then Gaussian process, we spent 5 lectures, right? So the modeling part, the selection of surrogate modeling part, we have spent enough time now. Obviously, this is not complete in the sense we cannot cover all the possible surrogate models that are there in the literature. For example, neural network is one of the surrogate models. We will not discuss that. Radial basis function is one of the surrogate models. We will not discuss that. Support vector regression is one of the surrogate models. We will not discuss that. And you can imagine any supervised machine learning algorithm, all of those are surrogate models. And obviously, it is not possible for us to discuss all of those. But the idea was that you should know the most used ones in reliability analysis, and polynomial chaos expansion and Kriging or Gaussian process happens to be those two the most popular ones, along with response surface, and we have discussed all three. Apart from selecting the surrogate model, there was one more aspect that was very important, and that was the sampling part. I mean, training sample generation part, which, because it's a simulator, which means you will decide where to generate training samples, and you will decide how many training samples to generate. This is a choice you will make. So the question is how many to generate and where to generate. And as if you remember in the first lecture of surrogate modeling, I said that that is also a very vital piece of puzzle in the whole surrogate modeling business. And that step is known as the design of experiments, and that's why you see DOE on the slide title. So DOE stands for design of experiments, which means you will design at which points to perform simulation. Simulation is a numerical experiment to generate training data. That is what you will decide. So the idea of today's lecture is that we will spend most of the time on design of experiments and then conclude our discussion on surrogate model. And if time permits, we'll go back and do the derivation from lambda to sigma for the Gaussian process. Okay, so that is kind of the idea for today. So with that background, let us start, and let us start with one small typo that I did yesterday. Some of you pointed out later, but not in the lecture. So this was the algorithm I wrote, right? And in this algorithm, there is one typo. It was lambda BB inverse, not transpose. So that was a typo. When deriving, we derived it inverse. But while writing the algorithm, I was looking back at the slides and writing. And that point, by mistakenly, I wrote transpose instead of inverse. So that should be a inverse. So if you look at the derivation is inverse. But while writing the algorithm, somehow I wrote it as transpose. So this should be inverse. Okay, so that was a typo. The remaining portion remain as it is. And as I said, if time permits, we will go to the derivation of the mean that you see here, the last line, how from the second last line, the last line comes, and derivation of the covariance. So how from lambda BB inverse, right? Again, the inverse is missing, I can see. How from lambda BB inverse, that term comes into picture. K star minus K transpose Cn inverse K. We'll go into that if time permits. Otherwise, it's a task for you to do. Okay. And if I do not do it, expect it as a homework problem, obviously in 4, not in 5. Okay. So this was the conclusion of Gaussian process. Now, let me tell one more thing, that Gaussian process is a vast area. There are different types of Gaussian process also. What we have discussed over the past 5 lectures is basically the most basic form of Gaussian process, which in machine learning terminology we call vanilla Gaussian process. But there are the sparse Gaussian process, there are the spectral Gaussian process, there are the graph Gaussian process, and there is a very rich literature on Gaussian process, which we are not going to cover because it's not a machine learning course but a reliability course. In case you are interested, you can go back to that probabilistic machine learning course. There we covered actually 3-4 types of Gaussian process as well. There we cover 3-4 types of Gaussian process as well. So if you are interested, you can go and check those videos out. But for the sake of this course, this is in the syllabus, others are not in the syllabus. Okay. So the vanilla Gaussian process is the only Gaussian process that is in the syllabus, because that is the only one that is used mostly. Okay. One more thing I did not discuss was the bottleneck. What is the computational cost of Gaussian process? It is cubic in number of training data. And that is quite obvious by the fact that you see Cn inverse. Cn is a n cross n matrix, and inverting a n cross n matrix, the cost is n cube, which means it is quite expensive. And if I go by the thumb rule, you cannot do it when you have more than 10,000 or 20,000 data points. More than that, so 20,000 means 20,000 cross 20,000. Inverting that is very difficult. I mean, you will not be able to do it on a simple laptop, let's say. Okay. But again, from reliability point of view, if you need 20,000 samples for your surrogate model, you better not use it. You use something else. You should look to minimize the number of sample points needed, because sample points means running simulation means computational cost. Okay. Okay. So that was the idea. I talked about 2 transformations that will be needed. I mean 2 matrix identity that will be needed to prove those. So that I have here today. The first one is the Sur matrix inversion identity that I was talking about. So if you have a matrix like A, B, C, D, and you want to find the inverse of that, this is the form it takes, where A, B, C, D, each of them are like matrices, right? I mean submatrices, right? So this is the form it takes, where M has a form of its own. So it's kind of complex, but there is a pattern that you will see, and as there is a pattern quite clearly, this will be useful. Okay. And the second expression that you see, that is known as the Woodbury matrix inversion lemma. And there, whenever you get a form like A plus UCV inverse, you can use this one. The whole idea is that this is useful if dimension of this whole matrix or dimension of A is much larger than the dimension of C. In that case, this is useful. And that means if why is it useful? That look at it. On the left hand side, you have to invert a matrix of dimension of the A. So A, let's say, is n cross n. On the right hand side, you are inverting a matrix of dimension. The middle one you see C. So C, that means is much smaller than, that's why it will be useful. And obviously you will ideally want A to be let's say some diagonal matrix. So if A is diagonal matrix, C is having a smaller dimension than A, then it is useful implementation wise. Otherwise it is useful in doing many things, deriving many things, such as the going from lambda to mu, lambda to sigma and mu. Okay. So this I'm keeping as it is. You can take a note of this. I will suggest you take a note of this too. The reason is that if I get time and come back, I will ask you for that. I don't want to go back to the slides. And at that point, you should be able to tell me, because I will need it. The second one I kind of remember, I guess. The first one is kind of complex to remember. Okay. For exam purpose, you don't need to memorize this, by the way. I mean, if this is there, it will be given in the question paper. But for now, I will suggest that you take a note of those things. Okay. Okay. So if you have taken a note of these 2 equations, which I might refer to at some point. Let us now start with design of experiments. Okay. So let us now start with design of experiments. Okay. So first we will talk about some of the most basic design of experiments, and the most basic one is factorial design. Okay. The first one is factorial design. Okay. So what is factorial design? In factorial design, you place training samples only at the corners, corner nodes or corners. That's where you place it. What does it mean? Suppose I have two variables, 2 and 3 variables is max I can visualize on this slide, right? So suppose I have two variables. Both the variables vary from -1 to +1. Okay. If it does not, you can bring it from -1 to +1. So in factorial design, let's say 2D. Okay. So the domain varies from -1 to +1. So that means my domain will be a square domain. Right? And my sample points will be 1, 2, 3, 4. Okay. So that means -1, comma -1, 1, comma -1, 1, comma 1, -1, comma 1. This is factorial design. Factorial design tells you, and this is again no proof. The idea is that these are the optimum samples. How did they arrive at that? They perform experiments, tried training something, and from that they arrived at it. What is the idea here? Can you guess? What is the intuition behind this kind of setup? You should not do extrapolation. Here with this setup, you are always doing interpolation, because you are taking the boundary points, right? So you are always doing interpolation, and that is kind of the motivation you can imagine, right? I mean, again, it is not mentioned, but my guess is that it is the motivation. Okay. In 3D, what will happen? How many points will you have in 3D? 8 corners, right? So in 3D, if I have to draw, sorry. So it will be something like ignore the axis for now, but you can understand what is this, right? And you will get the 8 corners as your point. Okay. In an n dimension, how many points will you have? N dimension, n input variables. 2 to the power n, which is a big number, right? If I have 100 variables, 2 to the power 100 is a very big number. So although in the lower dimension it feels like it's a very sparse kind of thing, using only 4 data, 8 data, but the way it grows is in exponent 2 to the power. As a result, you will not be able to use it for problems which are, let's say, I don't know, 50 dimension, let's say. You will not be able to use that, right? You will not be able to have the corners of that in 50 dimension. Okay, but this is the most basic one, the oldest one perhaps, and at one point it was used a lot. Okay, and this is mostly used with response surface method, by the way. By the time PCE and kriging came into picture, this was obsolete. But with response surface method, this was very, very common. Okay. Okay, you are getting confused with spatial points. These are not space. These are random variables. So random variables, each random variables are independent. If they are not, you will make them independent, and each independent random variables will have a bound in which they vary. Gaussian, you can argue that it does not have a bound. It does. I mean, practically -3 to +3, standard Gaussian. So it does in that sense, right? So each variable has a bound. You take that bound, make it -1 to +1, you will end up with this. You are getting confused because you are thinking an irregular domain in space. It's not space. It's the random variable dimension. It's the probability space, not the space. Okay. Correct. So if you know that this is the range in which the random variable varies, what is the steps in surrogate modeling? You will train a surrogate model, and then you will want it to predict the reliability index or the probability of failure. How do you get the probability of failure using a surrogate model? You do a MCS by using the surrogate model, not right? Now for MCS, you will generate samples. Now you have all those samples will be inside this range. They will never be outside, because that's how you have selected this bound. I mean, hopefully, right? So that means you are looking at interpolation, right? Again, for Gaussian, if you take -3 and +3 and scale it, in a million samples, you might get few which are beyond those. But the idea is that will be very less. So in that sense, so it will be predominantly interpolation that you will be doing during computing the probability of failure during the sampling process, during using this surrogate model. Right? Clear? So this was the factorial design. Now the time when factorial design came, people were working in lower dimension. In the lower dimension, people realized that okay, factorial design is giving too less a point in lower dimension, 4 point, 8 point, right? So they said, why not increase the point? Okay, and there comes central composite design. So the second one is central composite design, or CCD, not the coffee one. Okay. CCD, right? So in CCD, what you do, as I said, it is an improvement over the factorial design. So in CCD, what you do is that you first do a factorial design and then enhance it. So you have these 4 points, right, from factorial design. This 4 point came from factorial design, the 4 corners. In CCD, you have additional points along with this. Along with that, you have this point, this point, this point, and this point, middle point of each of the edges. Okay. Along with that, there is one more point. Yes. This one. Okay. So the factorial design plus the center of the edges plus the center of the overall domain. What is the total number of points in a generic sense? In this case, 9, obviously, but in a generic sense, n dimension. What? What is the total number of points for the n dimension? See what is happening. Think about it. 2 to the power n will remain. That everyone agrees. Plus each axis is having 2 points, top and bottom. So if n axis will have 2 n points, right? Plus the center. So 2 to the power n plus 2n plus 1. This 1 sometimes is written as alpha, where the central point is taken again and again. But that is only useful when you are doing actual experiment. In actual experiment, the central point is repeated because it is noisy, right? So for the same point, you will get different data, different values. But for our case, it is 2 to the power n plus 2n plus 1. There is no point repeating a point because simulation is deterministic, it will give the same value, useless, right? So generalizing it, the total is 2 to the power n plus 2n plus 1. And quite naturally, 2 to the power n was intractable. This is even more, so this is even more intractable if there exists something known as more intractable. But this is intractable, right? If factorial design is intractable, CCD is going to be intractable because it is always having more points, right? Clear? Now these were the primitive ones, these two, okay? Now let us come to the next stage of design of experiments. These are not used nowadays. If someone is using this, they have not read the current literature, okay? So moving ahead, modern, yeah, you can say modern schemes for designing experiments, okay? So modern schemes for designing experiments, what do you think is important for designing experiments? How do you think you should sample these points? Forget about these two schemes, but in a common sense manner. What do you think you should do? Uniformly? Okay, create a grid and then every point. You were saying something about FA? That is a quadrature point, and Gauss points will not work in, Gauss quadrature does not work in n dimension.
मतलब जैसे यहाँ पर हम बीच में we can there are 4 squares, right? So we put.
But why do we take quadrature point? Because what is the use of quadrature point we have covered in this course? Can you tell me?
We can use it for interpolation.
No, quadrature point is used because we solve the integration numerically.
Why am I taking?
No, that I am coming later. So there is a motivation behind the quadrature point in the FEM because there is an integral problem you are solving, and in integration you are going to do it numerically, and if you do it numerically, you look into the convergence of this summation as an integration, and when you look into convergence of summation and integration, you came up with these optimal points, which is in the orthogonal polynomials. I talked about it, right? You saw, and you come up with that. So that is the motivation of using quadrature point there. In this case, you talked about quadrature point. How and why? What is the motivation you are also telling me?
I'm not talking exactly about the quadrature point.
Okay.
But let's say I have 4 squares in 2D. I can make it 4 squares separate domains. And if I take
no, you do not have 4 square. You have 1 square. You are seeing 4 because I have drawn the axis as -1 and +1. You have 1 square, or you have infinite square.
Just for 2 dimensions. If I take one block.
No, even for 2 dimensions, you have 1 square. Where are you saying 4 square?
Just because of the axis.
But the axis is I have assigned. Axis does not exist. So if I have to generalize it, you are saying that you will first create number of squares. That's what you are saying. So you have to create. How many squares will you create? Because what he said was exactly that. He said I will sample uniformly. That means he is creating squares, and he is creating k squared squares. K and k square. You are saying no, you will create 4 squares, not k square, right? That's what you are saying? Okay, 4 square. Then
just take the central point. Centroid of
each square. Okay, then
that will give me the points.
Okay, so why 4 square? Why not 8 square? Why not 9 square? How did you arrive at this number 4?
It's varying from -1 to 1 to intuition is
no, minus 1, 0.2, minus 0.25, minus 0.5, minus 2. I mean, I can go right like that. So how do you, why this 4? I mean, there has to be some logic, right? What is your logic? I want to understand.
I was relating it to the FEM part.
Even in FEM, why 4? Let's go to FEM. Why 4? FEM also number of elements you decide based on convergence study. You just do not arbitrarily take 4, right? So how are you relating it to FEM?
Generally, we integration with non-dimensional.
Correct. So that is the non-parametric parameterization you were saying, that we go to the parametric element, right? Correct. But then you, even in that, that is what you do it for the element. You go from -1 to +1, right? And then because it is 2D, you do a Gauss quadrature with 3.5 point. That's what you do, right? 3-point quadrature rule, 5-point quadrature rule, those things you do. But those quadrature rule are based on the integration, not based on anything other than that. So you are in the correct direction, so I am discussing it, but not there yet. Anyone else? What should you do? We have 2 suggestions till now. One is we can do it uniformly. That means not uniform randomly, but I mean equidistant, Lin space kind of thing. And then they agree node, right? And the other suggestion is that we will divide into 4 and we can take inspiration from finite element and take quadrature points. Yes, quadrature points are for integration to summation, but that's fine. Let's take those points. Right? Both of these are correct and both of these are wrong, but both are in the right direction. Okay, so any other suggestions? Maybe generalize it, try to generalize it, because both of these are correct, I said. So let's take the correct part and try to generalize it. For example, he said that we should uniformly do it. Why do you think that came to your mind? What is the logic behind that? To do it uniformly.
I think of giving more weightage to the boundary. So that's what taking uniform.
Actually, what you are doing intuitively, but I will come to that later. Anyone else? What are you doing here? Why are you doing it? Actually, what both of them suggested, especially what he suggested, I will say, is known as exploration. That your training samples would be well spaced over the whole domain. It's because then you have information from the whole domain, and that information will allow the model to learn better. So that is a kind of exploration strategy, which is known as space filling strategy. The space could be uniformly filled as much as possible, right? But what is the drawback of that? If I cannot do A2 per dimension, how can I do K per dimension? 2 to the power n will become K to the power n. So doing it equidistantly is not an option, but to uniformly fill the space is an option. Somehow you want to generate samples even in 1000 dimension that will kind of uniformly fill the space, right? You can imagine using uniform random sampling in this -1 to +1 for 1000 dimension directly. So that way you are deciding how many samples to generate, and whatever you generate is kind of uniformly distributed over the whole 1000 dimensional space. But doing it manually in that manner will not work. Same holds for what you suggested. If you do by quadrature rule, the one we're saying quadrature rule does not scale for the exact same reason beyond 10 dimension. So again, in a high dimensional space, quadrature rule will not work, but it will be better than what he suggested. But it will not generalize to more thing. So the key takeaway for you should be that samples should be generated in such a way such that it should fill the space. So that is known as exploration or space filling algorithm. Okay. So modern DO is, again I am using the term modern, but it is not so modern also. This is also outdated kind of, but okay. Modern DO is use space filling strategy. Okay, which means you should try to fill the space more or less uniformly, which means nothing, there is no bias, right? Which means that you have information throughout the domain and hopefully then it will generalize better your model, right? But what do you think is the potential limitation of this? I mean, because you are doing space filling directly, its scaling will not be that big a problem because you are not limiting to 2 to the power n or k to the power n, something like that. But still the number of points needed will be higher and you are not exploiting any additional information that might be available to you. Sometimes there are additional information that are available to you, and what kind of information I will come to that. So if there are additional information available to you, you should be able to use those. Okay. So now coming to what additional information we might have. Can you guess? Yes, but for training a surrogate model, that might not be the important criteria. But anything else that you might have in some cases, or you might be able to find out? Let us take one example, okay? Let us take one example. Suppose I have a function, 1D function, okay, which is of the form okay, possible. I might have a function like this. Let us do space filling. Okay, let's see. And I will take uniform. First sample, second sample, third sample, fourth sample, fifth sample, sixth sample, seventh sample, eighth sample, ninth sample. What will you get when you try to train a model with this? 0. If I have taken the 0 point, you will get a 0 line. That no matter what the input is, it is 0. But it is a space filling strategy. Yes, you can. What you can do is, well, let me refine it more. Okay, so you decide to refine it even further. That okay, this is not good. So let us refine that. So refining, you are taking this point, this point, this point, this point, this point, this point. What will happen? The smaller peaks will now be captured, but the actual peak is gone. You will not be able to capture actual peak until and unless you place 3-4 points here. Adaptive meshing, you were talking about finite element, you never talked about adaptive meshing. This is adaptive meshing strategy, right? Wherever there is a high gradient, you place more samples there, right? Same thing can be used here, that wherever there is a high gradient, I should place samples there, and wherever the change in gradient is less, there can be less number of samples. Let us make it even more concrete with one more example. Suppose I have a problem or a function in this case. Right? In this case, you should have point here, I mean ideally, if you know this function. And then maybe corresponding to this, you should have 10 points. And then point here. Right? If I place the points in this manner, then it will probably be able to learn the function quite accurately. Which means you should place more points where information is more. Where the information available to you is more. That information in this example is in form of gradient. Right? But it can be some other statistical measure also. And I'll give you an example of that. Okay. But the long story short is that you should exploit any information that you have or can gather for the function you are trying to approximate. And this is known as the exploitation. You should exploit any information, I said, so exploitation. So the first one was exploration. This is exploitation. This means sample place more samples at locations having more information. Right? This is what it means. Different information is actually more information. If you go to information theoretic, so when you call information, given the previous sample, how much more information your new sample is given, or what additional information you are getting. Okay, so in that sense. Okay, but only exploitation will also not work, because with only exploitation, what will happen? You can only perform well in the places where you already have some data, and based on that it is information. Away from the data, it will start performing badly. That's what exploitation means. But if you only do exploitation, it means you are playing safe. You are only repeating things that you already know. You are not taking risk. Exploration means you are taking risk, and that might reward you. For example, you are interested in machine learning. Let's get it. But you are not studying finite element or CFD. You should study finite element and CFD, and maybe you know that the intersection of machine learning and CFD is where the main innovation can happen. So exploration means you know machine learning, okay, now I will do CFD. I know CFD, I will do machine learning. FEM, I know FEM, I will do biology. I know biology, I will do liberal arts. This is exploration. You are exploring everything possible. Only exploring is bad. Now you are not connecting the information, they are random and all those things, right? Exploitation means I know machine learning, I will stick to this. I don't care what is others. That is also bad. Ideal scenario will be a good balance between exploration and exploitation. So all the modern DOEs, and these are the modern ones, try to balance exploration with exploitation. Okay. Modern DOE balances exploration and exploitation. Okay. Now, last thing in DOE, from Gaussian process, we did it for last 5 lectures. Can we use Gaussian process to do design of experiments? And this is the last thing that we'll discuss in design of experiments. I talked about exploitation, right? So keep that in mind and think. Can you think how Gaussian process can be used for sampling additional or generating additional samples? Let us go step by step and see. So suppose I have a function that takes the following form. Okay. This is the actual function. I have samples here, 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 and here, 4 samples. Okay. In Gaussian process, what will I get as a final result? The algorithm was written in the first slide today, but what is the final output? Covariance and mean at a given test point, right? Now I have 1000 test points from here to here. In this range, I have 1000 test points. So for each test point, what will I get? A mean and variance, right? So if I plot the mean, how will it look? Go back to lecture 2, lecture 3, where I was showing those means, lecture 3 mainly, of GP. Remember, the mean will actually try to be something that is emulating this original curve. You remember that all the GPs, and I said wherever you have, you push it, and that's how you get it, right? So the mean will be something like, I mean, it will not be exact, obviously. Maybe something like this, right? You agree? Now coming to the standard deviation, variance, or the uncertainty interval. Remember what is uncertainty interval? The band. So what we will do is we will draw the upper bound and lower bound. I mean, drawing the band is better, but I cannot draw it. Okay, I'm not that good an artist. I'm a useless artist, but let's draw the upper limit and lower limit. How do you get the upper limit? Mean plus 2 times sigma, actually generally 95%. So because Gaussian process, each point is a Gaussian, and in Gaussian distribution, mean plus 1.96 sigma gives you 95 plus minus. Okay, so let's say 2. So mean plus 2 sigma. So how do you think mean of that 2 sigma bound, mean plus 2 sigma will look like? It will be above, but any specific feature of that you can tell me about? For example, what will be the sigma at this point? Let's say at this point, what will be the sigma? Almost 0. At this point, at this point, at this point, 0, almost 0. Actually, the sigma y, to be more specific, sigma y square will be the actual one, variance, but let's say the sigma y is very small, so 0. And away from this, increase. So uncertainty bound will probably be something like I mean, I'm drawing the upper bound, keep that in mind. Right? The lower bound similarly the same property. It will actually be symmetric because of the Gaussian property, each point. But as I am drawing it, it need not look symmetric, but you should know it is almost symmetric. Something like this. And if I draw a shaded area between these orange lines, that's your confidence interval. Right? From this, what can you decide? This uncertainty tells you at which location the uncertainty is maximum. So the next sample can be at the location having maximum predictive uncertainty. That means the Gaussian process, the uncertainty can be used to decide in an adaptive manner where to next perform an experiment. So you start with 4 points maybe uniformly exploration. Based on that you build a Gaussian process, predict at those 1 million points or 1000 points. Based on that you check which point has the maximum uncertainty. That point is your next training sample, so run the simulator at that point. Now you have 5 points, retrain your model with those 5 points and continue. It will slowly refine your Gaussian process. So the uncertainty that we are capturing is actually useful. And the moment you capture the uncertainty there, I mean the moment you place a sample there, uncertainty will go to 0. Because it collapses, right? So the idea is that next sample will probably be here, right? So this should be your next training sample. Okay. So the idea is that one way of exploitation is to place samples where uncertainty is maximum, right? Okay. So clearly I will not have time to the derivation. So let us conclude the surrogate modeling part only. Okay. So now you got some idea about design of experiments. You already got some idea about surrogate modeling. So how will you do the reliability analysis to conclude? Let us repeat from where we started. So now to start with, you will have a limit state function, right? You will use DOE to generate samples, training samples. Third is you will train a model, which is a surrogate model that maps from X to Y. So this is basically surrogate model. Step 4, generate samples from the distribution. This is for not testing, you are in reliability course, for evaluating the probability of failure. So this should from the distribution, right? That means we are going to do MCS, for doing MCS to be more specific. 5 and last, PF by MCS on M. So you will now do MCS, but not on the actual simulator, which is expensive, but on the surrogate model, right? So you will not do simulation, the actual simulation. You cannot do a million simulation, but you can query your surrogate model a million times. It will take fraction of seconds, and from there you will compute the probability of failure. So these are the broad 5 steps that you will have to do for reliability analysis using surrogate model. Let me repeat once more. So to start with, you will know the distribution of the random variable, right? PDFs. You will know the limit state function, right? And obviously you will know what are the sources of randomness. I mean, that's, you know PDF, that means you know what are the random variables. So you will first do design of experiment to generate training samples, and that is where actual simulation will be needed. Using those generated samples, you will train a surrogate model, be it a GP, be it a PCE, be it a RSM. You do that. Okay. Once that is done, your training is done. You now are ready to go to MCS. But you will not do MCS on the actual simulator, that's expensive. That's why we need surrogate model. So you will generate these samples randomly, a million samples or whatever. You know how to decide that number of samples now. You have done the simulation part, COV, coefficient of variation, right? So you generate those samples and now evaluate those samples using your surrogate model and check whether the threshold has crossed or not. Calculate the number of failure points. Find the ratio of number of failures by total number of experiments. That's your probability of failure, right? So this is how you do reliability analysis using surrogate model. Okay. Any question? So do this derivation. Anyways, I'll give it in the homework, but where is it? This one. Okay. I mean, not this one, but using this derived this one and this one. Okay. It is a good idea to also derive this too, by the way. You will get it online, but it's a good idea. Okay. So generally this is homework 0 in ProbML. Okay. Okay. Okay, then we'll stop here. Surrogate modeling is done. We are done with component reliability analysis. It took us 30 lectures, right, which is expected. That's the main part. The remaining 12 lectures will be on system reliability, will be on time dependent reliability, will be on reliability based design optimization. So next lecture, I'm thinking I'll start with RVDO and RDO. That's the easier one. Let's get done with it. Then we'll go to the other two aspects. Okay. Any doubt, question? No? Okay. Thank you.